Hi everyone, welcome back to part 3 of our facility planning series. I'm Belias. Today we will look at the continuous space location problems. We will learn the media method, how to deal with the real world problems using contour lines, and how to use linear programming tricks for software like games. Let's start. In continuous space, you don't just choose between city A, B, or C. You can put your new buildings any XY coordinate on the map. In math gives you endless choice. But in real life, math doesn't know what the length looks like. A formula might give you a perfect spot, but when you check the map, it might be in a lake or on a highway. So remember, the best mathematical point isn't always the point you can actually use. Before we find the best spot, we must decide how to measure a distance. There are two main ways. First, rectilinear, so-called Manhattan distance. The formula is in here. This is like walking around the city blocks. You can walk through a building, so you walk over and up. We add absolute differences of the coordinates. Second is Euclidean distance. This uses classical Pythagorean theorem. This is straight line distance, exactly like a bird flies. Today we are going to look at the single facility mini-sum problem. The goal is simple, make total weight distance small as possible. Our formula looks like in here. X is our new building coordinates, XY. Pi I are the buildings we already have, and WI is our rates. This is usually the number of trips multiplied the cost of each trip. We want to sum all these trips to be small as possible. In here, I'm explaining step-by-step median method. First, list the coordinates in increasing order with their corresponding weights. Then find the x median. After that, find the y median and the optimal location. Combination of the found x and y medians provides the optimal facility location. To solve these using rectilinear distance, we use median method. Let's look at this campus example, the food truck problem. A food truck wants to find the best permanent parking spot to serve three main places: library, dormitories, and engineering building. We have the XY coordinates for each building. We also know the average number of daily student trips, that is our weights, WR. Because students walk on sidewalk, we must use rectilinear distance. Here's how the median method works step by step. Step 1, find the target number. We add up all our daily trips to get total weight. 10 plus 20 plus 15 is 45. We divide that by 2 to get 22.5. We need to find the exact point where our running total reaches or passes 22.5. Finding the x median, we list our buildings by their x coordinates from smallest to largest, 2, 5, and nothing. Then we keep a running total of the weights. At x is equal to 2, we have 10. At x is equal to 5, we have 20, and to get 30. 30 is bigger than our target, so target of 22.5, so our best x is equals to 5. Step 3 is the find y median. We do the exact same thing for y coordinates, order them the smallest to largest to 5, 8, add them, add up the weights. At y is equal to 2, we have 20. At y is equal to 5, we have 15 to get 35. And we crossed 22.5 again. So our best y is equal to 5. Our perfect food truck location is exactly at 5 to 5 location. Doing this by hand was easy, but In real world with hundreds of buildings, we use computers programs. But there is a problem. Direct linear distance formula use absolute values. The computer programs cannot easily solve absolute values. To fix this, we change the formula into straight line. We remove the absolute values by adding positive and negative variables for each building. X positive I for positive change and X negative I for negative change. This lets us write our distance using X positive I minus X negative I plus X minus and is equals to XI. When we write this out for our food truck problem, here's the exact math model you would use in your studies. Our goal is to minimize x, which is the sum of all weights multiplied by their variables. This here minimizes the cost and so on. Then we add our x-axis rules and y-axis rules. That says number cannot be negative. This is the exact math happening in the background. And again, we find x bar and y bar is equals to 5 and 5. Now let's go back to our leg problem. What if the coordinate 5 and 5 we just found is right in the middle of a decorative compass water fountain? The truck cannot park there. This is where the contour line method helps. Instead of just guessing where to move the truck, we can draw map with rings or contour lines. These lines show the cost penalty as you move away from the perfect center. If you have to move the next ring to find dry parking spot, you know exactly how much extra walking distance you are giving to students. This helps you make your smart choice. And this is the visualized version. To really understand this cost penalty, look at this map. On the left, you have a possible food truck location. It is not the perfect map point near the dorms, but it is close. You can see the penalty is only an extra 8.04. That is very good compromise. But look at the map on the right. If we park the truck far up the north, we cross many rings, and our penalty jumps into 75.78. By looking at the math this way, you can work around real-world problems without making students walk too far. All right, let's change topics. Everything we just did in the median method was for rectilinear distance, walking on sidewalks. But what if we are using drones? What if we are using straight line Euclidean distance? The easiest way to solve this is gravity method, also called centroid method. Instead of finding the median, we find the weight average of the coordinates. In here, you can see the formula. When we use food truck data, we get 255 divided by 45, which is 5.78. Doing the same for y-axis, we find 4.33. Notice the difference. The median method gave us exactly 5.5. The gravity method finds us 5.67 and 4.33. Because it minimizes squared Euclidean distance, so it's act like physical gravity. The heavy weight of the dorms, which is 23, literally pulls the y coordinates down towards it. Here's a secret that confuses many of us. The gravity method is actually just a close guess. Because regular Euclidean distance uses square root, The true perfect location isn't a simple average. To find absolute perfect point for Euclidean distance, we must use the Wiesfeld iterative method. The idea is to use greater method to answer a starting guess. Then we run it through a loop. We update the location step by step using weighted averages, but we put the actual distance into the bottom part of the fraction. With every loop, the point gets closer and closer until the reach of the true perfect spot. In here, again, food truck problem. Step 0 is we start our first guesses gravity method points we found in other example. X1 is 5.78 and the Y1 is 4.33. Step 1 is the first iteration step. We calculate the straight line Euclidean distance di from our starting point to library, dorms, and the engineering building. Step 2 is we put those distance into Wiesfeld formula in here. When we do the math for just one loop, our new x becomes 5.81 and our y becomes 3.70. The track is moving. You would then take a new point. This will become our starting point. Calculate the distance again and run the loop again and again until the numbers stop changing. That is when you know you have found the perfect spot. In our next video, we will look at the advanced location model, what happens when we need to place many buildings at the same time, and a route good between all of them. And that's all for today. Thank you for listening. See you in the next video.